Now let us look at first law in open systems. Uh, Again, in open system, we can divide the entire spectrum into two parts, which is steady and unsteady. So what does steady mean? Steady means that the properties of the system are constant with respect to time. So none of the properties like volume, pressure, temperature, etc., or internal energy, etc., these do not change with respect to time. So that is steady, and unsteady is at least one property change with respect to time. Especially here, we say system is steady or not by just looking at the mass. If the because in open system we have mass interaction, so if the net mass interaction is zero, that means the amount of mass that is coming in into the system and going out is same, then we can say that it is steady. This is not like a universal law or anything. This is how we see if a particular system is steady or not in problem solving. This is just a hint, because most of the problems here are based on mass. We say steady or unsteady based on mass. And for unsteady, at least one property change with respect to time. So it doesn't mean that all properties need to change with respect to time. At least if one property is changing, then it is an unsteady system. And then another important thing, which is uniform. So in our case, in I think as far as I have seen, all problems are uniform case. We do not have the properties changing with respect to x, y, z. But if in some case they have given it is a non-uniform system, that means that the properties are a function. Sorry, the properties are a function of x, y, z. So with respect to space, the properties change. So let's see at the steady state case. So in a steady state case, this is our system. The green one represents the control volume system. In our open system cases, we use control volume analysis, whereas in closed system cases, we use control mass analysis, because that is how things will become easy in respect to cases. So in constant volume, everything that enters until it goes out of the system, it is part of our system. Once it goes out, it's of no matter to us. So I represents the inlet and E represents the exit. So all the properties of the incoming incoming fluid are represented by a subscript I, and similarly the outgoing fluid properties are given by a subscript E. So first we do the mass balance, because these are open system, and this being steady, dm by dt of the control volume is equal to 0. So your net mass input rate and the net mass output rate is equal to the sum of net mass input and output is equal to 0. So mi dot is equal to me dot is equal to m, and then we apply the steady energy balance equation. If for the energy balance equation, the amount of energy that is coming into the system is m dot into m dot into h1 plus c1 square by 2000 plus gz1 by 1000 plus q dot is equal to similarly plus work done. So let's look at it a little more. So m dot, your uh, mass of the fluid that is entering or exiting, which are both same in this case, and h1 plus c1 square by 2000 plus gz by 1000. You can write this as hi for more convenience. So that means that these are the properties at the incoming, that is h represents enthalpy, c represents velocity in meter per second, and g is your acceleration due to gravity, which is equal to 9.8, and z is the potential height head that is giving the potential energy, which is measured in meters. So this is important, the units in which this equation is simplified, so that the SI units of speed and Z can directly be induced, and H is in kilojoule per kg and m dot is kg per second, whereas this Q is the net heat interaction, which is in kg per second or in watts, and it's equal to right hand side. Yes, that's QE. Uh, Plus work done by the control volume. in kilojoule per second. Here, one thing that needs to be understood is this work done uh, is not the entire work done. It is actually the work done is divided into two parts. One is the work done by control volume, which we are seeing here, and the other one is flow work, which is equal to PV. And when we introduce PV and then take to the other side, our first law, which consists of internal energy plus PV, it changes into enthalpy because U plus PV is equal to H. So that is the reason why we have H in these equations and not U. And then reversible open system work is VDP, whereas in the closed it is PDV. Here it is VDP. So for a constant pressure, it is equal to 0, and constant volume V into P2 minus P1, and constant temperature P1 V1 on V2 by V1, same as this is same as closed system. And for adiabatic, this is the extra factor that needs to be multiplied, that is gamma into P1 V1 minus P2 V2 by gamma minus 1. And for a polytropic process, it is N into P1 V1 minus P2 V2 by N minus 1. And here, instead of constant pressure, constant volume processes, we have other terms that come up in questions, which are like nozzle, discharge, or a compressor, turbine, throttle, condenser, evaporator, or boiler. So these have some basic assumptions, and if enough data is not given in the question, these assumptions can be assumed. But if data is given, so that has to be considered. I'll give an example. For example, in a nozzle is usually used to convert the enthalpy into velocity. So there is no work done or no heat transfer. So Q and W is equal to 0, and change in potential energy is also equal to 0. So, and we are considering C1 is equal to 0. So this is an assumption that we're considering, but if in the question C1 is given like equal to 30 meter per second, that has to be considered and solved in the SFW, and we are going to get this equation like C2 is equal to 2000 into H2 minus H1, and H2 and H1 is CPT2 minus CPT1 if ideal gas. And then for a compressor or turbine, these are usually work consuming or work producing devices respectively. So again, here we consider it as adiabatic. So Q is equal to 0 and change it kinetic and potential energy is equal to 0. So that reduces the equations to H2 minus H1 is equal to W for a turbine. So that will be by the system or positive work. H1 minus H2 is equal to work done on the system in a compressor. So that will be a negative work. So, but if it is given that the change in velocities or there is heat transfer or heat loss, so that has to be considered and put that into the SFW. But if nothing is mentioned, only your enthalpies are given, you can directly consider these assumptions and finally come up with these equations. And then again in a throttle, so throttling is an important process to understand. This is a constant enthalpy process, throttling. So H2 is equal to H1. So there is no work done or there is no heat loss in a throttle, but the enthalpy is conserved, and the enthalpy is conserved such that for in an ideal gas, in a throttle, your temperature remains constant because H is a function of temperature around, because we have earlier seen that H is equal to CPT and U is equal to CVT. So this or DH is equal to CPDT. These are specific properties. I'm not considering mass. Du is equal to CPDT. Yeah, sorry, CVDT. So that's the reason. So whenever you see a throttle and ideal gas, you have this equation has to strike. And then for a condenser and condenser, evaporator or boilers, we usually lose heat. And we do not produce any work or we do not give any work. So the heat loss or heat gain is to be measured by change in enthalpy. So again, here there is no loss in kinetic energy, potential energy, or work. So again, as I said before, if there is some values given, that has to be considered. Next, let's come to the unsteady case. So here the properties change with respect to time. So so if you see, if m dot I and m dot d are not equal, you can say the system is unsteady. So this requires a little bit of solving using equation. Direct formulas cannot be applied. So for example, first you need to apply the conservation of mass equation. So dm by dt of the control volume. So one important point is here there is 1 and 2. That means that initially the system has properties 1, and finally after time dt the properties are 2. So whenever you have to find the initial and final properties of the system, we use the subscripts 1 and 2, and I and d are given to the properties of incoming fluid and outgoing fluid respectively. So dm by dt of the control volume is equal to m dot I minus m dot e. That is m2 minus m1 is equal to m dot I minus m dot e into delta t. So this is one important way. And then for energy conservation, again dE by dt is equal to we are writing dE by dt because we still haven't considered this assumption of no kinetic energy or no potential energy change in the system. So here again we have to understand that if we are considering the kinetic energy and potential energies are same for the fluid entering and exiting, then we can directly cancel, we cannot directly cancel this. Okay, now let's look at the energy conservation. In the energy conservation equations, dE by dt of the control volume is equal to net energy input through the incoming fluid plus heat transfer minus the net energy input through the exiting flow plus the work interaction between the system and the surrounding. So if you do not have any velocities, if the flow has negligible velocities and the potential is also negligible at 0, then we can directly remove this, and then the equation becomes mihi plus qi is minus mehe plus w dot cv. One important thing that we have to understand is if in the equation it is given that ci is equal to cv and zi is equal to ze, and that doesn't mean that we can directly cancel this as in the case before, because mi and me are not same. So there will be a part of CI that will be remaining, or there will be external additional kinetic energy that is being removed from the system. So then these values have to be inputted, and the process then the analysis has to be done. But if it is given that neglect KE, PE, or there are no values for CI and CE given in the entire CI, CE or ZI, ZE, then we can consider them as zeros and we can remove that. And then now if we are considering no kinetic and potential energy changes for the system, this is for the system, there is no change in kinetic and potential energies, then we have seen that E can be replaced by U and the equation becomes this. So U2 minus U1, so after a specific time, if you want to find what is the internal energy, then U2 is equal to U1 plus delta T into this factor. Next, one important thing to understand is free expansion. What is free expansion? For example, if there is this system, let me draw it again. Okay, let's say initially there is this system which is properly insulated, so there is no heat loss, and there is a wall separating this entire into two parts, and in one there is V1, V2, and here there is pressure P1 and T1, and in this it is vacuum. And now we are saying that this wall is being removed. So this will go to the state 2, which will be of this. We have V1 plus V2 and some pressure P2 and T2. right? So what has to be understood here is that the work done by the system is zero. For example, if you consider this as your control volume, now the same amount of gas uh, is now occupying this, or control mass, let's say control mass system, this is the control mass system, and the same control mass system is now occupying here, so the volume is increasing. It is very easy to say that there is PdV work, and yes, there is PdV work because there is change in both pressure and volume, but though PdV is not equal to zero, work done is equal to zero because there is no resistance to the movement of this air. uh, so once there is no resistance, we cannot say that there is any work, because we know from the definitions in mechanics that work is done only when there is resistance for that work to be done. And then because Q is equal to zero, there is no heat loss from the entire system, and work is equal to zero, Du is equal to zero. That means T1 is equal to T2. So T1 is equal to, so we know what is T2, we know V1 plus V2. So P2 can be found directly from ideal gas equation because we keep N same. So we can find pressure. Okay, now let's go into the formula. Let's go into the problem solving. Now let's look at question